Hello my beautiful students, so welcome back to a new session with KCET Masterstroke series. By following this session you can get top 1000 rank in overall Karnataka in KCET examination. So yes, today we are going to proceed with the next chapter, that is electrochemistry. So without further delay, let's get started, and don't forget to make a proper note while watching this video. So after this video definitely we will come up with a live session containing all the previous year question, and we will also trigger your doubts that you will keep putting in the comment section. Yes, so let's proceed. So here you can see this is a weightage year wise that is given here. So you can see the number of question that is coming from this chapter in different year. It's so high weightage, right? So next, one thing that I wanted to tell, if you are really preparing for KCET, if your target is to get a good rank in KCET, please enroll yourself in ABHYAS KCET test series. Here you will get 35 mock tests and you will get some PYQs that is of free of cost. So whoever has already enrolled themselves in ABHYAS KCET test series, they are getting this add-ons benefits in this particular test series. So now a little bit continuity along with this test series. Just let me tell you, my dear, it's all about a test series, right? It's a, like, you will get the mock test, it will give you the idea what type of situation or what type of question you may face during the KCET examination. But if you are really preparing, if you really have a proper target about the KCET examination, you must have a structured plan related to this, right? A proper schedule related to this, where you may need to watch some one-shot videos as well, right? It's not all about all the time just writing one examination. It's all about the conceptual clarity, right? So we are working hard chapter wise. Definitely in chemistry I'm working hard along with the ABHYAS KCET test series. I'm working hard so that I can give you a proper schedule so that you can go ahead with the KCET preparation with a little more spice. Okay, so please, I want you student also, please comment me below if you need that type of help or support from us. We are ready to bring those type of supports for you people. So please comment me below if you need those type of things. Yes, let's proceed further. So here in the electrochemistry, we will study it in 3 parts. Okay, so here you can see in the part 1 we will study the galvanic cell, Nernst equation, and in the part 2 we will study electrolytic cell and electrolysis and conductance of electrolytic solution. Okay, next you can see part 3 we are going to proceed with the batteries, fuel cell and corrosion. These are the overall things. Okay, so let me just tell you, my dear, whenever you are just targeting any chapter, so now if you are really planning that yes, I have to start with the NCERT studying and thoroughly I have to go all the lines, all the sentence, then my dear, this is not the perfect time to go through the NCERT in a well manner for chemistry. Rather, whatever you learnt, it's the time to apply, right? So please focus on application part. Okay, focus on how much you can solve. Okay, so whenever it comes to the matter of solve, then if you feel like I don't know the chapter, then you must see the one-shot videos. Okay, and that's the reason why Masterstroke is relevant to you. Okay, so yes, let's proceed further. First we will proceed with the galvanic cell and Nernst equation. In galvanic cell we will study the construction and working principle of the galvanic cell. We will proceed with the cell notation. We will proceed with the measurement of electrode potential. Next, calculation of cell EMF. Okay, that's related to the galvanic cell. And here, while discussing about the Nernst equation, we will definitely learn what is Nernst equation, and we will proceed with the equilibrium constant and Gibbs free energy. Okay, so let's proceed. First we will start what is basically the galvanic cell. So galvanic cell is a type of cell that converts chemical energy to the electrical energy. It's a spontaneous process. Del G value is 0. The example is definitely Daniell cell. Okay, So this is a very beautiful example of the galvanic cell or Daniel cell, better to say, because here we are using zinc and copper, right? So now let me just explain this thing well in detail for you people. Okay, so first what basically happens in this case, you need to learn, you need to understand the concept behind every cell, what's actually going on. So whenever a cell, a Daniel cell, it comes, it is constructed of two different cells, two different half cell, better to say. One is anode, one is cathode. Okay, so this particular cell is cathode, this is anode, right? So whenever it comes to the matter of anode and cathode, please remember anox and red cat. What I said? Anox and red cat. So let me just write it down here. Always remember anox and red cat. Okay, what does it mean? It means oxidation takes place in anode, and here reduction takes place in cathode. Okay, so these are the things that you have to remember. Okay, so here in the anode oxidation takes place, here in the cathode reduction takes place. Okay, so first this is the main thing. Then what will be oxidized, what will be reduced, that you need to understand. So I am putting one zinc rod in a solution that is containing zinc salt itself, zinc ion itself. Okay, zinc rod I am putting into the solution of zinc itself. Okay, so here the solution that I am using, that is basically Zn2+. So this is basically ZnSO4 solution. Okay, and here copper is dipped in copper sulfate solution, CuSO4 solution. Right, now let me just tell you, so here oxidation takes place, means zinc, if it gets oxidized, what will happen? Zinc here in the rod, it is Zn0 oxidation state. So what it does, it comes to the solution in the form of Zn2+ and it leaves 2 electron. Okay, it leaves 2 electron. So now in this particular solution I am having more and more Zn2+ ion, SO4 2- ion, and zinc is continuously, it's leaving 2 electron. This 2 electron will be carried forward through this wire and it will come to here, this another cell. So what is happening here? Oxidation takes place. Right, now what is happening here? The 2 electron that is released by zinc, the 2 electron that is released by zinc, it will come to the solution. It will come to the solution here in this case. In this solution, I am having so many copper 2+ ion, Cu2+ ion, and also SO4 2- ion. So this 2 electron will be taken by Cu2+, and if Cu2+ takes up 2 electron, then it will be converted to Cu0 and it will be deposited on the particular rod, right? So what is happening basically? Zinc is getting converted to Zn2+ because oxidation is taking place, and while coming to the Zn2+, it is releasing 2 electron that will travel through this wire. It will come to the next half cell, it will reach this solution, it will take up Cu2+ and it will convert Cu2+ to Cu0, and that Cu0 will be deposited on the copper rod, right? So this is the scenario that is happening. So with time what we will see, that zinc rod, it is getting thinner, right? It's getting thinner because zinc in the form of iron, it is coming to the solution, and copper with time we will get to see it's getting thicker because copper from the solution itself, it is getting deposited. So if I want to write the anode and cathode reaction individually, so let me just write anode reaction. So anode reaction is basically Zn will be converted to Zn2+ plus 2 electron And if we write the cathode reaction, this is basically Cu2 plus will takes up this 2 electron and it will be converted to Cu. Okay, overall cell reaction if you write, it will something like Zn plus Cu2 plus will give you Zn2 plus Cu. It's something like this. This is the overall cell reaction. Okay, so for this case, for this half cell, definitely oxidation is going on. So oxidation half cell, this is reduction half cell. Okay, now what is basically happening for this case? Also one E means electromotive force is generated. For this case also one electromotive force is generated. How it is designated? Let me show you. So for this case, for this half cell, the electromotive cell, it is generated as E0 of Zn is getting converted to Zn2 plus, right? For this case, for this half cell, it can be represented as E0 of Cu2 plus is getting converted to Cu, right? So now for this case, for this particular case, it is a oxidation potential. It is oxidation potential. For this case, it is reduction potential. Right? So now, one more thing that I want to tell, that if you want to convert oxidation potential to reduction potential value, okay, what I am telling, if you want to convert the oxidation potential to reduction potential value, you just have to add one negative sign. Okay, so oxidation potential, or better to say reduction potential if I write, reduction potential is nothing but the negative of oxidation potential. Okay, so from here for this particular case I can write E0 of Zn2 plus, right? This is the oxidation potential, right? So this particular thing I can write in the form of minus E0 of Zn2 plus of Zn. That will give you the reduction potential value. Okay, so this is how you can also convert from oxidation potential to reduction potential. So this is the entire galvanic cell that you have to remember. And here you can see the role of salt bridge here is very important. Okay, one more thing before that, let me tell you, my dear. So the the movement of electron is basically from the zinc rod to copper rod. Right, the movement of electron is from the zinc rod to copper rod. So the movement of current is taken as the opposite direction of the electron, right? So movement of the current is taken as from the copper to zinc. Okay, this is possible only if it is a galvanic cell. Okay, galvanic cell, the process is spontaneous and this is the reaction that takes place. I guess you understood this. Let's proceed with the salt bridge concept. Salt bridge is something very vital, because without salt bridge you can't even construct the cell, because you are having two different half cell, right? You are having two different half cells. So once you are having two different half cells, then if you don't put the salt bridge or if you don't connect them, the circuit itself will be not completed, right? So the main function of the salt bridge is to prepare the circuit. Okay, it creates a proper circuit, it connects the two half cell, right? This is the first thing. Okay, now another thing is in the salt bridge what we do, it's a U-shaped tube. In that case we put some agar-agar gel and we put some KCl, KNO3, ammonium nitrate, this type of salt, in which case like those salts only we put. For those, the movement of the both cation and anion are similar. Okay, means if I put KCl, the movement of K plus and Cl minus should be similar. Okay, mobility, ionic mobility should be similar. Okay, now what does it do? Like what we have to do with the mobility of the ions? Basically, whenever, let's say, why to put two different half cell? Let's put two different liquid in a single cell, right? In a single container. Okay, why to make the system so complicated, right? So whenever you are just putting copper sulfate and zinc sulfate in a single solution, so basically what happens here, let's say all the positive charge will accumulate in a same liquid, all the negative charge will be accumulated like that. Okay, so these particular thing will be generated whenever two liquid will be mixed, whenever salt bridge will not used. Okay, so as a result of this particular phenomenon is called liquid junction potential formation. Okay, as a result of this type of liquid junction potential formation, the cell efficiency decreases. So whatever the current we are getting, means why I should run this cell? I have to get some electricity. That's my point of view, right? So from the electrolytic cell, I need some chemical energy. I need some energy, right? So that energy, if it is getting decreased because of some liquid junction potential formation, so this is not my profit, right? So in order to decrease or to prevent this liquid junction potential formation, we put this salt bridge out there. Okay, I guess it's clear now. Let's proceed further a little bit. Okay, this is how you should represent your cell. See, zinc from the solid state, it is getting converted to Zn2+. Zn2+ is in the aqueous media, right? If the concentration is also given, then you can just write it in the bracket. And this double slash, it represents the salt bridge. Okay, and next cell, from the Cu2+, it is getting converted to Cu. So this is how you should actually proceed with the cell notation. I guess it's clear. Let's proceed further. Okay, so now here you can see a potential difference develops between the electrode and the electrolyte is called electrode potential. Means, as I told you, once you just connect the circuit, then one potential difference will be generated, and that case we call it electrode potential. When the concentration of all the species, let's say here also zinc sulfate and here also copper sulfate, we are keeping it as 1 molar, means unity. Okay, then whatever the electrode potential will be generated, it is called as standard electrode potential. So when it is called as standard electrode potential, when this solution and this solution, both the solution, the species, they are taken in unity concentration, means let's say 1 molar, like that. Okay, next, standard reduction potential are now called as standard electrode potential. Means for this case, as I told you, for this case, the oxidation potential you are getting, because oxidation is taking place here, right? Because from Zn it is getting converted to Zn2+. What is this? This is oxidation potential, right? But in accordance to IUPAC convention, we take the reduction potential value always. Okay, so but I am getting the oxidation potential value. So how to convert it? Just put one negative sign, you will get the reduction potential value. That's it. Okay, the reduction potential value is basically taken as a standard value. Okay, so like this is in accordance to the convention. Okay, so let's proceed further. Okay, so now we can proceed according to convention of a half cell called standard hydrogen electrode represented by, okay, we will study standard hydrogen electrode and we will just know how it works and what is the role of the standard hydrogen electrode. Okay, so basically standard hydrogen electrode is whenever you are just making a cell with the hydrogen. Okay, so for this case, by convention itself, it is taken as whenever a standard hydrogen electrode potential is always 0 at all temperature. It is convention. Okay, so let's proceed. Here we will see like what is the role of the standard hydrogen electrode while finding out the measurement of a electrode potential of a particular metal. Let's say I don't know the electrode potential of the zinc electrode, okay, and I know the electrode potential of the hydrogen, that is 0, right? So what we do basically, if we are using this as an anode, then what happens, we take the acidic solution. Okay, we take a solution of acid, 1 molar solution of HCl. Okay, now here we are putting some platinum surface within it in this particular electrode. That platinum surface is to it is basically providing the surface area for the hydrogen adsorption. Now we are having one inlet. Here you can see through this we pass hydrogen gas. Okay, so once the hydrogen gas is passed here, so the hydrogen gas will come and it will sit on the surface of the platinum surface, right? So platinum surface is playing a role of an inert electrode, right? It is not working in the redox reaction. It is not taking part in the redox reaction. Who is taking part? The hydrogen itself, right? The hydrogen itself is taking part. Platinum is just providing the surface. Okay, so this is I am taking as anode, and here I am taking zinc as a cathode, right? So now whatever, once we connect them, some amount we will get. Okay, some amount of EMF we will get. Okay, so always remember E cell is basically equals to E0 cathode minus anode, right? Cathode minus anode. Now this cathode value we don't know. The cathode value is, let's say zinc is unknown, or whatever the metal you are putting, that is unknown, right? So that thing we don't know, right? But hydrogen we know, and E cell value we know, right? So then taking it as X, we can find it out. E cell equals to cathode minus anode. Anode value you put as 0. This you take as X. Rest of them you will get it. Okay. So now here you can see it is measured with the help of a reference electrode as the standard hydrogen electrode. So here SHE is used as a standard hydrogen electrode. So SHE or standard hydrogen electrode, it is helping out to find out the electrode potential of the zinc electrode, like that. Next you can see the standard electrode potential of an electrode can be measured by pairing it with SHE and measuring the cell potential of the resulting galvanic cell. That's what I just told you. Okay. Here this is the formula I told you. E cell equals to E of cathode minus E of anode. If you are putting hydrogen SHE in the anode, put the value here 0, right? And here also E cell value something you will get out of the cell, right? Put it here. So E cathode you will get nicely. Okay, I guess it's clear to you. Let's proceed. Okay, one question. Cu plus 2Ag plus gives Cu2 plus 2Ag. First write the half cell reaction. Okay. Okay, if I write the half cell, first I will write the anode half cell. Anode reaction. Okay, what happens in the anode? In anode, oxidation takes place, right? So oxidation, where oxidation takes place, you can see Cu is getting converted to Cu2 plus, right? So Cu from the solid state, it is getting converted to Cu2 plus in the aqueous media, and it is leaving 2 electron as well. Okay, now if you write the cathode reaction, then basically what is happening here? 2Ag plus, that is from the aqueous, it is getting converted to 2Ag, that is of solid form. Okay, this is the half cell reaction A. Okay, now let's put B. What is B? That is a cell notation. So we know how to represent the cell notation. Here you can see. So anode will come first. So copper from the solid state, it is getting converted to Cu2 plus. Cu2 plus is in the aqueous state. Then the cell will be divided by a salt bridge, right? Next, what is basically happening? Ag plus aqueous, it is getting converted to Ag solid. That is a cell notation you can proceed with. Okay, let's proceed. Expression to calculate the EMF of the cell. Okay, expression to calculate the EMF. So EMF of a cell is basically equals to E0 of cathode minus E0 of anode, right? So what is cathode? This one. So E0 of Ag plus to Ag. Now whenever you are writing E0 of anode, be careful, this is oxidation, right? Please write here in the form of reduction potential. So E0 of Cu2 plus of Cu, or you can write E0 of Ag plus of Ag minus of E0 of Cu2 plus, in case you are having oxidation potential value. Okay, I guess this is clear to you. Let's proceed further. Okay, so Nernst equation. So this is to calculate the EMF. Okay, so here you can see for electrode and for cell, both the cases you can apply the Nernst equation. So for electrode, this is the Nernst equation you can use. M of n plus is getting converted to m. This is for the electrode, okay, not for the cell. Okay, this is the form RT by NF ln m by mn plus. Okay, and whenever it comes to the matter of a cell, let's say this is my cell, and here also you will get it in the form of cell, right? Here you will see, always remember product by reactant, so Ni2 plus divided by Ag plus whole square. Whenever why we are not taking the Ag and nickel, because they are in the solid state. Okay, so this is the equation for the cell itself. I guess it's clear. Let's proceed. Okay, so here whenever it comes to the matter of RT, R into T divided by NF, for this case n value is 2 basically for this case, but in general here we use NF, right? N can vary, so RT by F, if you convert this ln to log, it will come 2.303. So RT by F into 2.303, it will come up to be 0.059 divided by n. Okay, rest of them is similar. Let's proceed. Okay, one numerical problem. Here we will see the application of Nernst equation. So here you can see the electrode potential of Cu electrode dipped in 0.025 molar CuSO4 solution at 298 Kelvin. That you have to find out. Okay, standard electrode reduction potential is given. Fine. So we will definitely start with a Nernst equation, right? So if I just write E equals to E0 minus 0.059 divided by 2 log of Cu dipped in Cu2 plus, right? Cu2 plus, because what is the equation is going on here? You know, Cu2 plus will be converted to Cu. It will takes up 2 electron and it will be converted to Cu. So Cu product by reactant, always remember. Okay, so now here you can see for the Cu we can take it as 1, right, because it's a solid state, right? So here let's put the value 0.34. E0 cell is 0.34 volt minus 0.059. Here you can see number of electron exchange, it is 2 log of any solid is taken as 1 divided by concentration of Cu2 plus is given as 0.025. Okay, so now if you just a little bit, let me just calculate 0.34 volt minus, if you calculate 0.0296, right? Okay, now if you put here, it will come as 1 by 0.25 means log 40. Okay, so log 40, if you calculate 4 into 10, 4 means log 2 square, right? Okay, so now overall if you calculate, this answer will come up to be something like log 40. You can calculate in this way. Log 40 means 4 into 10, right? So log 2 square minus, sorry, plus log 10. Log 10 means 1, right? So here log 2 means 0.3, okay, whole square plus 1. Like that you can just proceed with the calculation and your answer will come up to be something like 0.2926 volt. Okay, so your answer is B. I guess you understood this direct application of Nernst equation. Okay, let's proceed further. Here you can see equilibrium constant. Okay, so whenever it is the equilibrium, then cell doesn't work, it stops working. Okay, E cell value becomes 0. Okay, and E0 cell if you want to calculate, then it will come to be, means in the same equation like what I am having basically, E cell equals to E0 cell minus 0.059 by n log K, right? This is the thing I am having, product by reactant concentration. Now if you put it as 0, okay, 0 equals to E0 cell minus 0.059 by N of log K. Now just take it that side and you will end up with this. Okay, so I guess it is clear to you, right? So let's proceed. Okay, this is the relation between gives free energy and E0 cell. Okay, NF minus NF E0 cell, and another is del G equals to minus 2.303 RT log K. Very important formula. Just make a note of it. We will practice some numerical. Okay, so here you can see one problem we have to solve here. H2 plus AgCl gives 2Ag plus HCl, okay. E0 cell at 25 degrees Celsius is given. Equilibrium constant we have to find out. Okay, it's very easy. Basically the relation we can use, that is E0 cell is basically equals to 0.059 divided by N into log K. That was the relation, right? So now put everything. K you have to find out, right? Equilibrium constant you have to find out, that is basically N into E0 cell divided by 0.059. Okay, let's put the value here. Log K is basically equals to 2 into 0.22 divided by 0.0591. Okay, so log K will come up to be something like, if you calculate this particular portion, it will come up to be something like 7.445. Okay, now if you just take anti-log, K equals to 10 power 7.4. Okay, so how actually you should find out this type of thing? So basically you can just target this type of thing like 10 power 7.4, right? I can go ahead with 10 power 7 plus 0.4, right? 10 power 7 into 10 power 0.2 whole square. Okay, so 10 power 7 you keep it as it is. 10 power 0.2 has its own value, like 10 power 0.2, 0.3, 0.5, 0.7. These values you have to remember. So if you put the value, you will get it. It will come something like, after doing the square, 2.8 something it comes. So here also I am directly writing here 2.8 into 10 power 7. This is your answer. Okay, I guess it's clear to you. Yes. Okay, let's proceed further. Okay, formulas to remember, as I told you, like cathode minus anode, there is a Nernst equation, there is a relation of the E0 cell with delta G and with the equilibrium constant. I guess it's clear to you. Let's proceed further. Okay, so let's enter into the part 2. Here you can see we are going through electrolytic cell and electrolytic conductance. In electrolytic cell, definitely Faraday's law, product of electrolysis, and difference between the galvanic cell and electrolytic cell, that we will proceed. And whenever it comes to the matter of electrolytic conductance, then we will start the factors affecting electrolytic conductance, important terms, definitions, symbols that we will study, formulas, variation of molar conductivity with dilutions, very important actually, and limiting molar conductivity, Kohl-Rush law, its application. Okay, so yeah, that's it. So yeah, let's proceed with the electrolytic cell at first. So what is electrolytic cell? It basically converts, just opposite to that of the galvanic cell, it converts the electrical energy to chemical energy. Okay, it is a non-spontaneous process. Del G value is positive, means you have to give some external electric supply and then the reaction, then the cell will be started. Okay, now anode is positive here. Okay, here anode is positive and cathode is negative, just opposite. Okay, it is used for like in order to get the pure metal. Okay, let's proceed. We will study Faraday's first law and second law. Statements are very important for the board people, and for the KCET aspirants, the formulas itself are very important, because utilizing those you can get some questions. Okay, so here you can see the first law is the amount of chemical reaction which occurs in any one of the electrode during the electrolysis by a current that is directly proportional to the quantity of the electricity passed. Okay, so here if you just write the statement, that is basically M equals to Z into IT. Z is called electrochemical equivalent. So Z can be represented as molar mass divided by N into Faraday's constant. Okay, note down the formula, it's important one. If you just proceed with the second law, then what is the second law? The amount of different substances that is liberated by the same quantity of electricity passed through the electrolytic solution, they are proportional to their equivalent weight. The mass of the, or the amount of the substance that is liberated, they are proportional to their equivalent mass if same quantity of electricity is passed. Okay, so for this is the formula M1 by M2, because M1 is directly proportional to E1, M2 is directly proportional to E2. So if you just put them together, M1 by M2 equals to E1 by E2. Okay, let's proceed with the problem. Okay, let's proceed with the problem. A certain quantity of electricity is passed through an aqueous solution of AgNO3 and cubic salt solution connected in series. The amount of silver deposited is 1.08 gram. The amount of copper deposited you have to find out. Atomic weight of copper and silver is given here. Okay, so let's at first find out the equivalent weight of silver. Okay, so equivalent weight, what is the formula? Equivalent weight of silver. Okay, so what is the formula? It's basically the atomic weight by N factor. Atomic weight of silver by N factor. Okay, so atomic weight of silver is 108 and N factor is 1. So equivalent weight is going to be 108 itself. Okay, now equivalent weight of copper, if I find out, it's 63.54 divided by N factor is 2. So I will get 31.77, right? So now what is the formula? M1 by M2 equals to E1 by E2. So M of Ag divided by M of Cu equals to E of Ag divided by E of Cu. Right? So M of Cu you have to calculate. So M of Cu is going to be M of Ag by E of Ag into E of Cu. Right? Now let's put the value here. So 1.08 gram divided by 108 gram into 31.77. So from here I am getting 0.01. So I am getting 0.3177 gram. That is the answer. Okay, so option B is going to be the correct one. I guess it is clear. Direct application of the second law. Okay. Okay, so here you can see the products of electrolysis. So if you are using the molten NaCl and if you are using the aqueous NaCl, the product of anode and cathode may vary. Okay, so once you are using the molten NaCl, the anode you will get the chlorine gas and at the cathode you will get the sodium metal. But if you are using aqueous, means diluted NaCl, then in the cathode itself you will get hydrogen gas. Yes, anode is similar. Okay, so look at the reaction at the cathode itself. Whenever you are using the molten one, sodium will get reduced and chlorine will get oxidized in the anode. But in case you are using the aqueous NaCl, then at the cathode hydrogen will be reduced. Water will be reduced. H2 will be reduced to H2 plus OH minus, right? And as a result of this you will get some hydrogen gas, and chlorine reaction is similar in the anode. Let's proceed. Here you can see dilute H2SO4 and the concentrated H2SO4. Again you will get the anode and cathode product different. For diluted you will get the H2 gas and O2 gas in the cathode and anode. Okay, and the reaction, as you can see, in cathode hydrogen will be reduced, right, and in the anode water will be oxidized. right? But whenever you are using the concentrated, water is not there, then SO4 2- in the anode will be oxidized. As a result of this anode product, you will get S2O8 2-. That is the oxidized version of SO4 2-. Okay, so let's proceed. Okay, one question. In electroplating, the metal to be electroplated is made at always in the cathode. Okay, so from the cathode itself, what happens? It undergoes reduction, right? It undergoes reduction. So as a result of this, on this metal you will get the coating of the other metal. Okay, so I guess it's clear to you. Here comes the difference between the galvanic cell and electrolytic cell. So here you can see any whatever in accordance to your marks, you can just put any 3 and you can just write down the difference for the board people I'm telling. So a galvanic cell produces electricity by chemical reaction occurring inside the cell, and electrolytic cell definitely it's like it requires electricity from outside. You have to put some electricity to drive the reaction inside. Okay, it converts chemical energy to electrical energy, and that one is electrical to chemical energy. This is a spontaneous, that is non-spontaneous. Here cathode anode abbreviation also gets changed. Cathode is positive here and anode is negative. There it is opposite, anode is negative, cathode is positive. Like this you can just proceed. Okay. Okay, so now we will proceed with the conductance of electrolytic cell. So the conductance of electrolytic cell by the ions present in the solution, it is called the electrolytic or ionic conductance. Okay, means the electricity that is generated by the ions present in the solution. Okay, not because of the free electron, because of the ions present in the solution. Okay, so now here you can see here what we will see when discussing about the factors affecting electrolytic conductance. First we will proceed with the nature of electrolyte added, then size of the ions, then nature of the solvent, concentration, next temperature. Okay, so if I just proceed with the nature of the electrolytes added, so definitely if you use the ionic solution, I mean ionic substance, like there can be different type of electrolyte, strong electrolyte and weak electrolyte, right? Strong electrolyte, they dissociates quickly and they gives more amount of ions and they will give more electricity, right? And weak electrolyte, they will not give more electricity definitely. Size of the ions produced, if the size, it actually affects the mobility. If the size is very small, then it can move move properly, and definitely also hydration effects are also there, that also taken into account. Then if you just proceed top to bottom of a periodic table, the size increases, okay, and hydration decreases, right? So bottom, I understand the size will be greater, but still this will give you more conductivity because hydration will be lesser. Okay, let me just tell you a little bit about this thing. If I just discuss about the lithium and sodium, and if I ask you which one will be having maximum conductivity, then my answer is sodium plus. Okay, why? Because you may tell that lithium is smaller size, it can move faster, but my dear, whenever you are putting water or any solvent, so lithium ion will be solvated. Lesser the size, smaller the size, more solvation, more hydration, right? As a result of this, I am running alone and I am running with this many people around me, right? It will be difficult for me. For lithium, it is the same case. Okay, lithium is smaller, I understand, but whenever it comes to the water, it is getting surrounded by so many water molecules, it's getting hydrated, right? So hydrated sphere becomes very big, right? So for the sodium is comparatively bigger than that of lithium, so hydration is lesser in sodium, right? So that's the reason sodium can move freely, right? So this is the thing you have to remember. Next, nature of the solvent and its viscosity. If in case I'm just taking a solvent that is very viscous, okay, so it's not possible for the ions to move freely, right? Concentration of the electrolyte, if you increase the concentration, definitely the conductance is expected to increase, that we will see later on. Temperature we will see that in case you are just increasing temperature, what happens, the kinetic energy of the ions, it increases, right? As a result of this, they can move faster and they can give you better conductivity, right? Let's proceed. Here comes some formulas. You can see resistance, resistivity. Resistance, I guess you know, rho into L by A. Rho is the resistivity out there, okay, and cell constant is called G star. G star is basically the length by the cross sectional area, okay. Conductance, you can see that is G, that is 1 by R, reciprocal of the resistance, and conductivity is the reciprocal of rho, that is kappa, okay. Molar conductivity is taken as lambda m, okay. Lambda m is basically kappa into 1000 by C, okay. Equivalent conductivity also may come. Equivalent conductivity is basically this. Here the concentration term we use as molarity, but whenever it comes to the term of equivalent conductivity, that concentration term is changed to normality, that's it, okay. Proceed. Which of the solution has the highest conductivity? So definitely first all the like concentration is similar, okay. You have to check the size, okay. So CH3CH, it's very weak electrolyte, right? So definitely that's not gonna be the answer. Now NaCl and HCl, okay, so HCl is definitely going to be the answer because it is a smaller in size, and H plus can move. Now you can ask me, H plus is even smaller, why the hydration doesn't take place? So for the H plus type of thing, H plus or OH minus is having the highest conductivity rate. Why? Because of the Grothus proton jump. H plus doesn't move, it jumps, okay. It jumps from one water molecule to another water molecule. H plus gets transferred, okay. So H plus you should not take it into account, rather whenever it comes to the matter of other salt, you should compare the hydration. So definitely HCl is going to be the highest answer, because KNO3 I am not telling further because NO3 minus is a big anion. It will again very hectic to move these big anions, right? I guess it's clear. Let's proceed. Variation of molar conductivity, okay. So here you can see molar conductivity increases with decrease in temperature for both strong and weak electrolyte. It is a very important point. If you just see conductivity, if you just look for the normal conductivity, conductivity increases with increase the concentration, but molar conductivity, it increases with decrease in concentration. Molar conductivity increases with decrease in concentration. Why? If you just simply look into the formula, here you can see this is molar conductivity, it is kappa by C, right? Molar conductivity is inversely proportional to C, right? So if you increase C, molar conductivity will decrease, right? So yeah, let's proceed. Okay, this is because total volume V of the solution containing 1 mole electrolyte, that is also a reason, because the V also increases. As you are increasing the molar conductivity, then V also increases, the volume, total volume also increases. That is one of the reason. Okay, so let's proceed. Variation of the conductivity. So conductivity always decreases. Conductivity, there is no issue. Conductivity always decreases with the decrease in concentration, or increases with increase in concentration. Okay, so this is very simple. The number of ions in unit volume, it increases if you increase concentration, thus the conductivity increases. But molar conductivity, whenever you are talking about, then volume itself also increases. That's the reason molar conductivity decreases with increase in concentration. Remember this thing, okay. So I guess it's clear to you. Let's proceed further. For weak electrolyte, molar conductivity for weak electrolyte, this is always this increases due to the increase in dissociation. Means it is in accordance to the Oswald's dilution law. In accordance to the Oswald dilution law, what we can tell that if you keep diluting and weak electrolyte, if you keep diluting a weak electrolyte, then the dissociation of ion will increase, right? The more amount of ion will come out, right? As a result of this, if more amount of ion comes, then molar conductivity increases, right? Now for strong electrolyte, here you can see it increases due to the increase in mobility of ions. Okay, so for strong electrolyte it increases very less, means for this case it is a huge change, you can see it's observed, but for strong electrolyte the change is not that much. Okay, for this case you can see an exponential change like that, but for this case you will see a straight line. Okay, in accordance to the Debye-Hückel-Onsager equation or Debye-Hückel equation. For Debye-Hückel equation, if you just plot lambda m versus root c graph, then you will get lambda m0 as a intercept and a as a slope. Okay, so here you can see this is the graph for the weak electrolyte. You can see the change. Okay, like as you are decreasing the concentration, this side represent decrease. As you are decreasing the concentration, the lambda m value is increasing like that. But for KCl, if you see, okay, then the steepness is not that much like that. Okay, now whenever you are getting this value, now you have to extrapolate this, right? Why you have to extrapolate? Because extrapolation means here your concentration is 0, almost 0, right? Here your concentration is 0. Hypothetically it's not possible. Infinite dilution or taking the concentration almost tends to 0, it's a hypothetical concept. So once you are getting the straight line curve by putting lesser concentration, then you can just extrapolate it and you can imagine the situation here when the concentration is almost 0 or concentration is 0. That time whatever the lambda m, whatever the molar conductivity you will get, that is called lambda m0 or limiting molar conductivity. So what is this? Limiting molar conductivity. That is nothing but the intercept. Okay, so what is limiting molar conductivity? Limiting molar conductivity is a conductivity of a strong electrolyte when it is infinitely diluted or the concentration tends to 0. Okay, so I guess it's clear what is the significance of the lambda m0. So for the strong electrolyte you can nicely get the lambda m0 value, means the conductance at infinite dilution. For strong electrolyte you can get by extrapolating it, but for the weak electrolyte, how will you get? You can see the nature of the graph, it's an exponential graph, right? It's an exponential in nature like that, right? So how will you get it? Right, it's not possible to get the molar conductivity, limiting molar conductivity for the weak electrolyte. How we should do then? We actually use the value of the strong electrolytes and we can calculate the weak electrolytes molar conductivity. So utilizing the lambda m0 of the strong electrolyte, you can actually calculate the limiting molar conductivity of the weak electrolyte. Okay, let's proceed. So here comes the Kohlrausch's law. So what is Kohlrausch's law? Direct application, I mean direct question also can come from the Kohlrausch law, like what is Kohlrausch law, like that. Okay, one application also they can ask. Okay, so first they are explaining what is limiting molar conductivity. This question comes for the board people, please remember that. So when concentration approaches 0, the molar conductivity is known as limiting molar conductivity. Okay, next here you can see Kohlrausch's law. This is limiting molar conductivity of an electrolyte can be represented in the form of sum of individual contribution of the anion and cation. Okay, so let me just tell you, my dear, whenever let's say whenever I'm having a very concentrated solution, let's say here one Na plus, here one Na plus, Cl minus, like that. These are very concentrated solution. The ions are very close to each other, right? Ions are very close to each other. So there comes different type of effect that restricts the movement of the ions, my dear, like electrophoretic effect. Those type of things are there that restrict the movement of the ions. Okay, they can't give individual contribution because sometimes they are affected by the neighbor ion, right? But whenever they are very much diluted or infinite diluted, let's say here I am having one Na plus, here I am having another Na plus, here I am having one Cl minus, so they are far apart from each other, right? So they can have their own contribution towards the conductivity. So that's what the cold rush law about. Okay, so it says that it can give all the cations, all the anions, they have their own contribution towards the electricity at infinite dilution. So if you just add them, you will get the limiting molar conductivity. So this is applicable for the strong electrolyte. Remember, utilizing the values, you can actually calculate the limiting molar conductivity of the weak electrolyte. Okay, so let's proceed. Here comes alpha. Alpha is basically degree of dissociation. Here comes one formula of alpha in the form of lambda m. So lambda m, molar conductivity divided by limiting molar conductivity, will also give you the value of alpha. Now dissociation constant of an acid, that can be represented by C alpha square by 1 minus alpha. It's from the 11th syllabus actually. So here in the alpha you can put the lambda m value, and you can simplify to get it like that. Okay, so this type of numerical you can face in the KCET. We will do. Okay, now here you can see to calculate lambda m0 for the weak electrolyte, we will see here in the next problem. See, NaCl, HCl and sodium acetate, all of them are strong electrolyte only. The values are given. All the values are, this value we got by extrapolating, right? Now calculate acetic acid. Acetic acid is a weak electrolyte. Okay, so how we should proceed? See, wait, let me change the ink. Lambda m0 of CH3COOH. Okay, so for this case, what we can do? See, we can break it down in the form of CH3COO minus plus lambda 0 of CH3CO, sorry, again I'm writing it, lambda 0 of H plus, right? Now few ions I will add and I will subtract as well, so it will not create any effect. So I am adding here, let's say lambda 0 of Na plus. Later on I will subtract. Okay, and I am adding, let's say, lambda 0 of Cl minus. Now let's subtract them. Lambda 0 of Na plus minus lambda 0 of Cl minus. Okay, there will be no change. Now just club them together. Lambda 0 of CH3COO minus plus lambda 0 of Na plus, right? Plus lambda 0 of H plus lambda 0 of Cl minus minus lambda 0 of Na plus lambda 0 of Cl minus. So for this case, here you can see lambda 0 of CH3COONA, this thing, right? CH3COONA, that value is given, plus lambda 0 of HCl is also given, minus lambda 0 of NaCl is also given. Now put the values together. So if I put them, 91 plus 425.9 minus 126.4, unit is Simon centimeter square mole inverse, right? So if you calculate them, it will come up to be something 390.5 Simon centimeter square mole inverse. Okay, your answer is D. I guess you understood this. Okay, let's proceed further. Okay, so this is my part 3. So here we will discuss about the batteries and about the fuel cell. Okay. And corrosion as well. So batteries, whenever we will discuss, it will come up to be primary batteries and secondary batteries. Okay, so batteries definitely primary and secondary. Here in the primary batteries, it means the reaction, it happens inside the battery only once. Okay, it cannot be reused. once it is done, then you have to throw it. Secondary batteries are rechargeable, okay. It can be recharged by current through the opposite direction, okay, and it can be used. Next you can see primary batteries example is dry cell and mercury cell, and secondary batteries example is red storage cell and nickel cadmium battery, okay. So we will see the equation. First is dry cell. Here you can see sometimes related to the anode reaction and cathode reaction also the question can come, okay. So dry cell you can see zinc will get oxidized at first in Zn2 plus, and in the cathode itself manganese dioxide, and in presence of ammonium ion, okay. Ammonia gas is released over there. And in the mercury cell what happens again, zinc in the form of OH minus, zinc in the presence of OH minus alkaline medium, it forms zinc oxide, and there in the cathode reaction mercurous oxide you are having in presence of water, it forms mercury, liquid mercury, okay. Remember the product that you are getting in anode and cathode, okay. Here you can see this is a lead storage battery, okay. Lead storage battery, lead will get oxidized here, it will form lead sulfate Pb2 plus, okay. In the cathode itself you can see PbO2, it will get converted to PbSO4, okay. Next in the nickel cadmium battery you can see cadmium will form the cadmium hydroxide in the anode, and their nickel oxide it will form the nickel hydroxide there, okay. This is a cathode reaction. Let's proceed. This is a nickel cadmium cell, okay. So this is the overall reaction actually, okay. Now here you can see this is a overall for the lead reaction, okay. Next you can see on charging, if you charge it then what happens, the battery reaction is reversed, this entire reaction will be reversed, okay. If you just put the electricity from the opposite direction, okay, then anode and cathode is converted into Pb and PbO2 respectively, okay. So this is for the recharging process. Proceed. Fuel cell, this is a I guess you know, because of the presence of methane, methanol, those type of thing, on being combusted, the energy can be converted, right, utilizing a galvanic cell orientation. So we can use hydrogen, methane, methanol, the electrical energy we can directly use in the fuel cell, okay. So most successful, that is the hydrogen with oxygen fuel cell, that is to form the water, okay, it forms water. Now here what happens basically in this particular cell, it is actually used in the Apollo space program. So in this cell H2 and O2 are bubbled through the porous carbon electrode. Here you will be having the electrode, and the H2 and O2 they are actually bubbled through the media, and concentrated aqueous NaOH solution will be there, okay. And the catalyst they are finely divided platinum or palladium metal, okay. They are incorporated into the electrodes for in order to increase the electrode reaction, because as you know, for those cases hydrogen and oxygen they can be adsorbed on the surface area of the platinum or palladium, right. So this is the fuel cell orientation, okay. So this is a reaction that takes place. Oxygen it forms OH minus, okay. In presence of water it takes up 4 electron. In the cathode it reduction process is taking place, and in anode what happens, hydrogen gas gets oxidized to water. Overall reaction H2 plus O2 is giving you water, okay. So this cell, the efficiency of cell is as much you are providing the supply of H2 and O2, the cell keeps going, okay. Let's proceed with the corrosion. So corrosion is a phenomenon. What happens basically, on the iron surface there comes a coating of iron oxide, right. So basically what happens on the iron surface, iron gets oxidized at first, it forms 2 electron, right. It forms 2 electron, and Fe2 plus through this water that is accumulated on the surface, it goes to the cathode end, okay. So here you can see here H plus or O2 is also present, okay. It gets converted to water further, Okay, and overall whenever it connects with oxygen, it forms Fe2O3, and that will give you the red colored that coatings of iron oxide that we call as rust. Okay, this is the corrosion. I guess it's clear to you. Yeah, let's proceed. Here you can see iron will be oxidized to Fe2 plus, and reduction also oxygen. Oxygen in presence of H plus, it forms water, and like from the atmosphere itself, this iron 2 plus, when it comes in contact of water, it forms basically the Fe2O3. That is the formula of rust. Okay, I guess it's clear. Okay, so that's all about the chapter, my dear. This is all about the electrochemistry in one shot lecture. So if you have any doubt, please comment me below, and please like, share and subscribe to get such more informative video, and make sure that you are also taking part in the live session so that your doubts can be clarified by me directly. Thank you for watching. Thank you so much.